Hi, so welcome today. We are, again, back up for today. If you have not finished the homework, make sure to finish the homework by tonight. Quiz will be available tomorrow from 8 a.m. to midnight. It will be you'll have two questions. One will be a Thevenin and one will be a superposition. So just note that it will have two questions on there for those two topics. And next Tuesday, again, the exam is going to be during the same time, but we will not be meeting in here. Where will we be meeting? In where? 210, which is the Engman lab. So just upstairs in 210. So it's called Engman lab on the outside. And we will be meeting there. You're welcome to bring your own laptops if you prefer to use that, or your tablets. And if not, you can utilize the computers there in the Engman lab. They do have a scanner, so if you have a home scanner that you've been using, instead you can use the one that they have there in the lab. It's a little slow, just to let you know, but there is an availability of a scanner in there. Otherwise, bring whatever you've used up to now to kind of upload your work. I'm fine with you using your phones to upload your own work. You do need to make sure you have your work submitted in order to get full credit, even if you do get the answer to be 100%. So you do need to show your work for it. Otherwise, you will not get credit. So I'll repeat that one again. You may not get credit for your exam if you just put an answer only and not showing your work for it. All right, any questions about the upcoming exam? You guys, yes?
Is there going to be like a Canvas announcement or something with the information for the exam?
More than I've already, like, what information do you want me to send in that? I can send an announcement, but what do you want in it?
I'm not sure, like we can use any online calculator, right?
Mm-hmm.
So like MATLAB's okay? Or
Mm-hmm.
okay.
Yeah.
Alright.
MATLAB's okay if you want to use MATLAB. Other online calculators, there's Wolfram is also another popular one. Yeah, you're welcome to use any of those. Any other clarification or questions or things you want me to send in the announcement? Is that pretty much it?
No, I just want to make sure I have like the right room number and stuff. I don't
Okay.
mess up.
I will send that number through an announcement, and then a little bit more clarification about what you can use and what you can bring. Pretty much you can use anything except for a circuit simulator and online help or peer help. So just as long as you're not utilizing any of those and you're using your own skills to create the solution, I'm fine with you using extra material. Okay.
Will you contact the CDA to let them know exam times so I can schedule my exam?
Come talk to me right after class. So if you have a CDA accommodation and you're not clear what you're gonna do, come talk to me. Okay.
Well, I called them to schedule the exam with them, and they said you hadn't put it into their system.
Yeah, correct. So I'll do it a little different. So come see me after. So if you are needing an accommodation for a particular environment, please come see me right after. I thought I sent you an email, so if not, then come see me after. Any other questions, concerns? Okay, we're gonna move to the next topic, which will not be on this exam, and then you'll have a homework due next Thursday for this topic. So this is gonna be op-amps. So going back to our fun little RoboBees. So with the RoboBee, remember these are really teeny tiny devices, and the signals that we get out of them are really teeny tiny because you have very small power source in there. So with that power source, the max signal or max amplitude you could have for anything within that is going to be very, very small. So what we want to do is amplify either a difference. So remember with the Wheatstone bridge, you can have a difference, but a lot of times it may be very, very small. It might be like 0.00001 or 0.00005, and you're like, well, that's such a small difference, and if I looked at all those numbers, it might be hard for me as a human to actually detect the differences. So what we want to do is actually amplify that value from a 0.0001 to maybe 1 volt, where it makes a lot more sense to us, and seeing the difference between 1 volt and 5 volts is a lot easier to interpret. And so this is called an amplifier, and we use a element called an op-amp to be able to amplify. So some of the other examples of where amplifying voltage or a voltage difference kind of can make a very big difference is that we have in this one, there's communication that happens between implanted pacemakers and an external device on the outside of your body. And again, you don't want to be carrying around a whole 12 volts of, 12 volts inside your body or 24 volts. So you don't want a really high voltage in your body. So most of the time, the power that is being supplied to devices such as this are really small. And so, it's usually operating with like a 1.5 volt battery in there. And so, or a 1.5 volt source, or a different kind of source where it's not being able to generate a ton of power or voltage. So what is done is that communication is done, and then the signal is amplified again, so that it can be something that we can interpret and make a big difference, or can understand it in a different way. This is an actual schematic of a typical op-amp. So these devices here that are in the circles are called a BJT transistor, and we are going to get to those in a little bit. So you'll learn a new element, which is the transistor element. What these do is operate in a way so that they actually amplify the signal that comes in, and they're made to work differently, or they're acting as a switch to let signals go through or not go through. So you have different stages. One is a differential amplifier, one's a high gain amplifier, and then a low input impedance amplifier that actually gives you, if you put on an external resistance, then it doesn't decrease your signal. And we're going to talk about that in a little bit with these op-amp configurations we get to. But kind of want to just show you, like, this is actually what an internal looks internally to the op-amp, what it looks like on the chips that you're going to work with. So the op-amp comes in these chips. So within there, you're going to have this, it's a symbol. It's represented by this triangular symbol. It has 2 inputs. So on here, you have what's called a non-inverting input. And on the amplifier symbol that you'll see in schematics, it will be a plus sign on that one. And then on the inverting input, you'll see in the schematic, it would have a negative little symbol by it. So these are your inputs. And then it has a positive power supply and negative power supply. So it has to be connected to power. In a circuit schematic, you usually will not see these drawn. So these are usually not drawn. But they are implied that they are there. So when you physically hook up the circuit, you need to know that you have to make sure you have power to the chip before it will even work. So make sure you are creating or putting on the chip. You're going to look at what's called a data sheet. And that is one thing I realized is not connected here. And on your data sheet, it will show you, so this little U shape is a little notch in the top of the chip. So that's how you know how to orient it. And then on the data sheet, each of these pins will be labeled of what they need to be connected to. 6, 7, and then it goes across on the bottom and counts upwards towards the top. So that would be how you would read which pin is which. So in this way, this would be your pin 1 that's to the left of the notch, and then this one would be pin 2, and so on. So here you can see that the VS is going to be what needs to be connected to your positive supply. And then on this one is pin 11 would be your negative supply. So you need to make sure you connect those, otherwise it will not work. And then you need to identify whichever op amp you're using, if you have more than one op amp on the chip, which ones are your inputs and which ones are your outputs. So you can see closely here, you can see that there's a plus side and a negative side. So in this case, this would be my negative input, and this one would be my positive input. And then my output would be taken from pin 1. So you have to hook up 2 inputs, and then you have 1 output. And in this case, there would be my output. So that's kind of what the schematic looks like for an op amp. And what it does is what we're going to talk about next. Any questions about looking at an op amp chip and understanding that there's some element in there that has 2 inputs and 1 output, and you have to supply power to it to make it work? Okay, so that's the takeaway from this. Okay. So op amp rules, when we look at actually analyzing this now, we have the plus side and we have the negative side. And these are our 2 inputs, and then we have our output over here. So what we assume is that no current flows in these. Assume no current into the inputs. And then on the output, we can assume this acts like a voltage source. And this will make our analysis to be a little bit easier. So there's kind of some vague things that are kind of going on inside of this op amp. But how does it work if I do put some signals? So again, you need to supply power to the right pins, a plus and a minus. So that's the first thing that you would do to the op amp, is give it power. And then it works by looking at the voltage on the plus side and the voltage on the negative side. And my output is going to be some, it's called internal gain. And it's just going to subtract off. So I call this VP for positive and VN for V negative. You're going to see this also as V plus and V minus. And what it does is it takes this internal gain value, which is approximately infinite, and it says that VP minus VN multiplied by that. So if I have a really large number, and VP minus VN in this case is what? VP minus VN. What is VN first off? What is the value here?
0.
0 volts, correct. So 0 volts on this side, 3 volts going in at Vn, so Vp minus Vn is,
3.
thank you, 3. 3 minus 0 for 3 volts. So this is going to be positive infinity, right? But realistically, it can't be, because it can only go as high as the supply voltages that I give it. So if this is the case, I have 3 volts and 0 volts. What would I see out of here instead of plus infinity? 10 volts, correct. So really just 10 volts. Okay, I'm going to change this. So what if I have this case instead, where I put ground on the positive side and I supply this with 3 volts. So you're going to also start to see a little bit different symbols. So sometimes it may be a dot like this with the value of 3 volts. What this means is that wherever that dot is actually connected to a power supply to ground. And those are the same, they mean the same thing. So in a schematic, if you see a line with an actual voltage to it, that means that it's actually a power source from that location to ground. So what will be my output here? Infinity times what value? 0 minus 3, thank you. So then I get minus infinity, but it can't be minus infinity, so it's really negative 10, correct. So what this is doing is, this is called a comparator or switch. And depending on which voltage is higher than the other one, it either gives you the plus 10 or the minus 10 out. So you notice with this, there's no other connection on the output back to the input. It's more simply just two inputs going in. Okay, and one other thing I wanted to mention, in a real op amp, this is kind of what you will see instead. You'll have an Rin, and then on the output, there'll be an output resistance and a voltage source. What does this configuration look like? Correct. And that's what it's doing. It has created a Thevenin of everything that's internal to it, which you saw was a pretty complicated circuit. And it models it with just a voltage source and a resistance. That's the Thevenin of it. So a lot of times on a data sheet, they'll give you this value of R out, and then they'll give you a gain value for the voltage source. And what that gain value means is it's just the voltage source value is that gain times the difference in the input. And so it gives you those two values on a data sheet along with this Rin value. And so what you need to know is, like, ideally, and what they typically are, is Rin is really big and R out is very small, almost 0. And you'll see it will be like 0 point something and it will be a very low value. Those amplifiers that aren't so good will be all the way up to like 1000 K. So they might have some resistance that you need to take into consideration. The gain will be really high. And again, you like a really high gain that's almost infinity. So we're going to use the ideal case where Rin is 0, Rin is infinite, R out is 0, and then you have a high gain So you're not going to have to worry about the internal model that this does. You just kind of want to know that these are here so that if you are not considering ideal, you will consider the effect that these have. And what they're going to do is affect, instead of having the exact voltage you would expect out, it might be instead of 4 volts, it might be, oh, it's 3.99 volts. And that might be why, is because, oh, I didn't consider some of these values in here. For your purpose, most of the time you're not going to even need to calculate these, but just in case you want to use these in a circuit, you need to kind of know that they might be there and the effect that they might have. Okay. All right, so we've already gone through this switch. So the switch or comparator. So the switch or the comparator only go to what we call the rails. They only go to the plus rail and the minus rail. So it's only going to be one or the other. So it's going to create an output that's usually like a square wave. If we have a sinusoidal signal, most of the time we want to amplify that to be a lot larger. So we're going to use a different configuration, and we're going to use something called feedback to be able to create that amplification. So these are the different kinds of configurations where you have feedback. So an inverting amplifier, the output of an inverting amplifier is going to be a negative gain value times your input. And so your output will be a negative value. That means if you have a sinusoid that goes up first and then down, the inversion of it is going to be going down first and then out. So if you were to compare those two on an oscilloscope, you would see that the output would be flipped from the input. It doesn't mean anything because it's just inverted. And so the negative for us just means an inversion when we're talking about amplification. So instead of a positive output, it gives you the same magnitude, it's just negative. So non-inverting is where you don't have that flip, and the output will be equal to a positive of the gain of the amplifier times the input. And I'm going to change the input here to just be Vn. A voltage follower just has that the output is equal to the input. And I'll talk about the benefit of a voltage follower in a minute. Summation is that you have two different inputs. And your output will be so I'm going to call them Vn1 and 2 and Vn2. And so your output will be a gain 1 times your Vn1 and adding it to a gain 2 times Vn2. And a difference or subtracting is when you have, again, two inputs. Don't need to do plus and a Vn2. And then your output is going to be a gain for one of them, and then subtract off the amplification of a gain 2, and then a non-inverting summer or summing. Oh, inverting summing, sorry. It's a negative of the addition of these two. And then a non-inverting is a positive of that. Gain 1 times V1. So hopefully their configuration title can kind of help you. Like inverting means that I have some gain and I get a flip of the answer. And then for non-inverting, I just have my gain times my input. Follower or buffer is just the same input going out. And then a summing is that it's a negative of the summation of those two. And non-inverting summer is the summation of those two with gain. And then a difference or subtracting is that they just are subtracted off each other. So what do these configurations look like? So this one is a non-inverting amplifier. So first goal is to be able to identify that this is a non-inverting amplifier. So how you identify is to locate where the input source is. So one, identify where the source is. All right, so this is going into which input terminal? The positive or the negative? Okay, so that's where you follow it into where it goes into the op amp. So input on this, and again, remember that dot means that it's a source that's a voltage supply or AC supply there that goes from that node to ground. So this goes into the positive side of the op amp. And then you need to identify, so actually I'll back up. So first identify, is it switch or feedback? So with feedback, there will be a path from output through some elements back to both ground and the input. Well, no, I'll just say from, that was too big. I'll just say path from output through elements back to input. That will be better, back to input. And then a switch is no path back to input. So that's the difference between having feedback and having a switch or comparator. So looking at this, I see that I do have a pathway. Here's my output, and I have a pathway here back to the input. So this has feedback. So I know where my input's coming in. Also, I only have one source. So I'm also going to check that when I'm doing this. How many sources? So I have one source. So this will have only one source. And we identified it says feedback and not a switch. So then you have to say, out of the one input, I'm going to have either non-inverting, inverting, or a voltage follower. So going back to these, inverting, actually I'll highlight them. So inverting, non-inverting, and voltage follower buffer. These three, only one source. So once I identify that I have just one source and I have feedback, I will then be able to narrow it down to those three configurations. So looking at the configurations, identifying where it's coming in. So if I come into the positive side, I can have non-inverting or a voltage follower. So the input into plus side is either a non-inverting, because it's coming in the plus, or follower. So then the difference between the non-inverting and follower is that the non-inverting has pathway from output to ground. To ground and input. Where the voltage follower only has a pathway from the output to the input. So that's the difference between the non-inverting and voltage follower. So input into the plus is non-inverting. Where's the source on this one? It's going into negative side, correct? So seeing it's negative and my source is here. So I've narrowed it down to the three options. Non-inverting, inverting, or follower. It's not a follower or non-inverting because it's going into the negative, so it's inverting. So this configuration will be your inverting amp. For the inverting summer, you have more than one input, and so this has 3 inputs. I should have set that up here. Let's see. 2 plus inputs, 2 plus different inputs. So you can have more than one, just 2. So as long as you have at least 2 or more, then it would be a summer or a difference. And on this one, it's going into the negative. So again, negative inverting. So inverting summing amp. Here I have 2 again. But I see on this that I have one go into the plus and one go into the negative. So because of this, this will be the configuration for a subtracting or difference. Difference amp. All right, and then this is the voltage follower. And on the voltage follower, you only have one pathway right back to the input. So input is also, again, going into the plus, one input going into the plus side, and then there's just pathway going back to the input, and so it's a follower and not a non-inverting amplifier. All right, these are drawn a little differently, but I could have just put like V1 here and V2 there and not had these, and that would have been the same thing. Going into the plus side, so plus is non-inverting, so non-inverting summer. Okay, you guys ready? Oh, I'm going to go over, before we do that, one more time the differences between them. So what is this one? It's a what? Which configuration? Hearing somebody say it. Say it a little louder. Thank you. Yep, it is a switch. Good job. Okay, so switch or comparator. So you can see there's nothing connected on the output, and so this would be so there could be something connected here, but it doesn't feed back to the input anyway. So even though it goes through ground, it still is not connected through resistance or wire to the input. All right, what is this one? Say it a little louder.
Non-inverting.
Thank you. Yes, non-inverting. So one input going into the plus side, and it has a pathway to both ground and the negative side. What's this one? Correct. Inverting. What's this one? Which kind of summing? Inverting summing, correct. And in comparison, this one is? So this one's going into the plus, so non-inverting. So that's the difference between those two. Summing. And this one went into the negative. All right, comparing those two, which is inverting and non-inverting summing, to this one, what is the bottom one? Yep, subtraction. So subtracting or difference. So this one has a signal on both in input and output, or I mean, negative input and the positive input. Okay. So this one is the voltage follower. And hopefully you can see that there's only a pathway back to the input and not to ground. So that's why it's a voltage follower. And for the voltage follower, the input comes into the positive terminal. So very brief comment is that all of these have feedback that's called negative feedback, which keeps the circuit stable. And so if you see that the feedback is actually coming, so this is the feedback portion, and that's going into the negative terminal. Here is your feedback portion, again going into the negative terminal. Feedback portion going to the negative terminal, and feedback going into the negative terminal. And here we have the feedback portion of it is again going into the negative side where it's tied in right here. And while the R3 and R4 are a voltage divider, they don't have feedback going into that positive terminal. So these are all called negative feedback, and it creates the stable system. So 50, I think it's 56, well, it's ECE 5615, 50, I think it's 5220 for mechanical engineering. 5220 goes into control systems. You talk about how you get to stable systems and why they're stable. And so you can use electrical engineering components like this to look at those types of systems for control, or other mechanical systems for control. But anyway, stability part of that is in that course if you have interest in that one. So classical control theory is where you get into that. All right, so now let's talk about what gain do we get out of these configurations. So going back to this one, and remember this we're going to treat like infinity. In reality, it will be whatever the supply is. So if it makes it easier. Well, no, let's do still infinity. So infinity, and then this was V. I like P and N instead of the little lines, but I'll label them here. What happens when I want to solve this for so VP in this case is V in, and Vn is going to be V out. So if I want to put my equation in terms of Vn is equal to something V out, what will that look like here? What happens to this V out over infinity?
Becomes 0.
It becomes 0. And Vn will equal V out. So that is how mathematically we get to Vn equals V out here. Okay. All right, so we're gonna look at a few different circuits now. This looks like it stretched. No, it still looks stretched, but okay, so all right, not sure what happened there. Go ahead and let's put in what you think this first configuration is. I think that should. So what configuration do you think this one is? Go ahead and put it in the poll. So I don't mean to call anybody out. So if you're comfortable saying why you think it's a subtracting. Anyone that put that, just why? What creates a subtraction one? Or why did you think it was? Anybody willing to share? As you're changing it. I'm curious because I want to help you see why it's not subtracting. Everybody's changing theirs. Okay. Nobody wants to speak up. Okay. So subtracting, you got to remember there's got to be two different sources. So that's the reason why it's not subtracting. There's only one source here. So when you look at this, this is what you identify as your input, which is only one input source. So not subtracting, and that's because there's only one source. And then it goes into the plus side, so it is non-inverting. So with one source, you can have 3 options. It can be a follower, or non-inverting, or inverting. And so the non-inverting and follower, sorry, there we go, is the plus side. And then there's only one option if it's on the negative side. So because it only has one source, we'll rule out that it's subtracting. Does that make sense? For those that put subtracting, hopefully that makes more sense now. Okay. So don't be embarrassed if you put that. It just is a learning experience. Okay, what's this one? Oh, let me bring that over. Okay, go ahead and, oh, sorry, that was supposed to be in further. There we go. Just waiting for somebody to put subtracting again. Can go through it again. Thank you. Hopefully my explanation helped. This is why this is great, anonymous, and if that's what you see, that's fine. I just want to help you see why that might not be correct. Because we have to do things wrong to be able to improve. So it's okay to be wrong, just not on a test. Be wrong before the test and then correct yourself before the test. Okay, great. It looks like everybody on there was correct for inverting. It is inverting. And the reason why is because it has one source and it goes into the negative terminal, so inverting. All right, let's look at this one. Big enough, but okay, go ahead and put what you think this one is. Somebody learned not subtracting. Thank you. You guys make me crack up. So great, yes. These are all correct, non-inverting. So we have one source and it goes into the plus, but we have the feedback that also goes ground to the input, and so it's not a follower, it is a non-inverting, or non-inverting, yes. Inverting. Okay, try this one. Sorry. Let's see that one. Okay. So this one that is here. Okay, great. So yes, correct for everyone, inverting. I am very happy to see that this RL did not throw anybody that did answer off, but may have thrown people that may not have answered. So source can be voltage source or current source. So that's okay that it's a current source this time. It is still one source, and it's going into the negative terminal. The RL is there, but it doesn't affect the op amp at all. It just affects how much current is going to the load. So as I said before, this V out becomes more like a fixed voltage. And so no matter what I do with changing the value of RL, the only thing the change in RL does is change the current, because that V out will stay fixed it acts more like that voltage source. All right, let's do this one. So now looking at this one, oh, that's not what I wanted to do. What do you think this configuration is? And correct, it is a non-inverting. Inverting. Forgot to put inverting. Inverting, but non-inverting. Okay, let's look at this one. I like the creativity going on there. So for this one, what is this circuit here? Thank you, yep, Wheatstone Bridge. So your signal actually is coming in on this top one. And then this is tied to ground here. This is a very common configuration that you guys may see as mechanical engineers, because a lot of times this would be a sensor and you're going to want to amplify that signal. And you can either compare it to ground, or you can put a fixed voltage down there, or you can use a difference amplifier and tie one of the inputs to A of the difference amplifier, one to B, and actually take the difference between those two signals instead. So those are the common configurations that you're gonna see a lot of times. So this one in particular, being grounded on the positive side, would go in, and this would be, somebody can just shout it out. What will this one be? Inverting, correct. What about this one? Here, I'm gonna let you guys do this one. That's actually none of them. So confused was right. So it's the same input, so it's not going to do a difference. So you need two different signals for that one. So this one was the tricky one. So you would have to actually solve this as a not known configuration, and then you would solve it from scratch, which we're not going to go into the details very much with that one. I won't expect you to be able to solve a new configuration. So the main goals of what you need to take away from the op-amp for this lecture is going back to identifying the different configurations, being able to understand how to identify them. Is it a comparator or does it have feedback? If it has feedback, which configuration is it? And then the next step we're going to move to is, if I identify it as an inverting amplifier, can I calculate what the output will be based on the configuration? Or in all of them. So the next thing we're going to go to is how much of the gain do we get? So going back to the non-inverting amplifier, the gain is based on the values for your R1 and R2. And so based on R1 and R2, you get that the gain, which is the G here, is R1 plus R2 over R2, or 1 plus R2 over R. Wait. Where's R1? Oh, R1's on the top, that's why. Okay. So you could write it either way. So in the inverting and non-inverting, this R1 resistor, which is the one that's feeding back into the amplifier, is going to be the main one that is determining the gain. So in this case, RF over RS, and then you have a negative for the inversion for the inverting one. And then for the inverting summer, it's going to be each gain is going to depend on the ratio of RF to whichever resistor is right by its input. So RF over R1 for input 1, input 2 will be RF over R2, and input 3 will be RF over R3, and then it would be a summation of each of those. What happened there? And those gains are all negative, so it's a negative of the summation of all of them. For the difference amplifier, you're going to have the R2 over R1 for your input 1, which is going into that side. And then on the other side, you're going to treat it like, so this is where superposition again can be used. So if I was to look at this with superposition, I have two sources. I can turn one off, turn the other one on. If I turn off V2 and leave on V1, it looks like an inverting amplifier. So that's where the gain comes from, is the inverting amplification of it. For V2, your input first goes through a voltage divider. So you have that the voltage here is the voltage across R4. And so the voltage divider would be V2 times R4 over R3 plus R4, which is where this term comes from, is the voltage division of that input. And then it looks like it's going into the positive input. If V1 is grounded, it looks like a non-inverting amplification. And so you just multiply it by the non-inverting one. So this is the non-inverting gain times the voltage division. The voltage follower we already went through, so Vin is pretty much equal to V out. And then this gain is going to be the non-inverting gain. Right, there we go. So the non-inverting gain, and then with the resistors going in, you can also create a division between RS1 and RS2. And so that's what these are, is dividers based on the location. And so this would be the non-inverting summer. So you can have this sheet very handy to be able to remember these gains. So once you identify what configuration it is, you can look at the values and actually figure out now how much amplification am I going to get. So going down, let's see, get some with some values here. RF is not given. We'll do this one. This one's easy. Okay, so far we've also only looked at a fixed value, like 4 volts, 5 volts, a DC value. The amplifier is great because it can also amplify a full signal. And any signal, you guys all had Math 2250, so I'm like thinking where you are. So with any signal, in Math 2250, you learn about the Fourier signal series. And in the Fourier series, what that does is it can map any arbitrary signal into very specific summations of a whole bunch of sinusoids. And then you can model that signal by a whole bunch of summations of sinusoids. So that's kind of a cool technique that you can then use that model for any type of signal that you are wanting to mathematically express. Once you get that, you can either, you can filter out, depending on what amplitudes you have for the specific frequencies, you can filter out at different frequencies so that you only are passing a very specific frequency range, and then you can amplify it. So you could pick a frequency here of one of the ones you want to like filter through, and then amplify the magnitude of that one so it then becomes the dominant portion of a particular signal. So this could be a summation of a whole bunch of sinusoids, even though it is expressed here as just one sinusoid, and it would amplify equally all of the amplitudes of each of those signals. So we're just going to give an example of one of them. So if I had 1.5 sine omega t, I put it into now, which configuration is this? Thank you. Inverting. And just so you don't have to go look above, the gain of that will be a negative R2 over R1. So what is my output here going to be? Here, I'll let you guys all put a value. This is bogus. I like that one too. It is a non-configurated op-amp. Okay, so go ahead and let's see. Try and get this more. Put the value for what V out would be here. So the gain here, those are correct for everyone except for the one that did take it back. Negative 10 would be, you would take the resistor, so you have to, even though they're labeled R2 and R1, you have to look at where they are in the circuit of that configuration. So you have to identify this located resistor as the one on the top versus this resistor location. So do make note if you're looking at that table that you know like where the resistor is, not just by the value, like R2 variable. Because those variables are just variable names. It's the location of 100K over 10K. So minus 10 times 1.5 will be minus 15 sine omega t. So now you guys can actually design even an amplifier. So say you wanted a gain of, so wait, I'll back up 1 second. Negative in front of this, what does that negative mean? Yeah, and I can't remember, so you did, yeah, I'm just gonna arbitrarily put this on here. So if my input is the red, I can't draw today, sorry. But the blue would be my output, would be just flipped from it. Well, it's gonna look. Okay, I will try and do better. Oh, I still didn't do a great job. So if that's my output, and then this would be like my input. So it would be just flipped opposite of that. So that's what the negative means. And then what if I put a resistor right here? Is that V out going to change? It will not change. So this does not affect it because the output of an op-amp acts like a voltage source. And if it was a voltage source there and I put an R load on it, all it's going to do is change the current. So it doesn't change the output. Let's see what else. What if I want to find what power is being consumed at that resistive load? What will that be?
V out squared over R.
And in this case, that would be 15 squared. So it would take the max, should I say max power? So the maximum is usually what I'm looking at when I look at designs, instead of like an average value. Because taking the average of this isn't gonna create like me getting and picking the right resistance value, because I need to make sure that it doesn't blow up. So 15 squared over 10K, whatever value that is. And then I would need to make sure that my rating for that resistor is high enough than the wattage there. Okay. All right, any questions about what we went over today with the op amps? Okay. All right, see you guys on Tuesday in the Engman lab.